as we said previously, we're going to use photoelectron spectra to measure ionization energies, and based on those ionization energies that we measure, we're going to present an electron configuration of lots of different atoms. So we saw this photoelectron spectrum previously, where it had 2 electrons in the 1s. Come on, PowerPoint. 2 electrons down here in the 1s. That's those over here at 126. 2 electrons in the 2s subshell. 6 electrons in the 2p subshell. That's this tall one at 531 ionization energy, megajoules per mole. And then this last one, 2 electrons in the 3s subshell. Come on, there we go. So there were 12 electrons total in this thing. It's magnesium. If we were to write the electron configuration, so this back here is an energy diagram. If we were to write an electron configuration of magnesium, we need to put those 12 electrons in the right shells and subshells and orbitals. We're going to get there. So knowing that this is the energies of orbitals of shells and subshells, meaning anytime you're looking at an energy plot, it's going to be 1s, and then 2s, and then 2p, and then 3s, and then 3p, and then 4s. That's the filling order that electrons will go go into an atom in. So we say that in the 1s subshell, there are 2 electrons. That little superscript 2 tells me there are 2 electrons from magnesium in the 1s subshell. So now we've got 10 electrons left to place. The next 2 go into 2s, so 1s2, 2s2. We've taken care of 4 electrons. P subshells can hold 6 electrons, so there are 6 of them in there. That's 10 that have been taken care of, and then an S can hold 2, 2, 4, 10, 12. This is the electron configuration of magnesium. So when I say, give me the electron configuration of any element, I'm wanting something like this: 1s2, 2s2, 2p6, 3s2, etc., if it's got more electrons than that. There's another way that you can write this electron configuration, and it's called the noble gas shortcut, the noble gas shorthand. So magnesium has the exact same configuration from here back. It has the exact same configuration as neon. Neon has the electron configuration 1s2, 2s2, 2p6, because that's a 6, because neon has 10 electrons total. So the neon part is identical to magnesium, and then the 3s2 is additional to magnesium. So we call those neon electrons core electrons, and we would call those 3s2 the valence electrons. Magnesium has 2 valence electrons, 10 core electrons. Core electrons, remember, are held tightly to the nucleus, are closest to the nucleus. They don't get involved in chemical reactions. When we wrap up this atomic structure stuff, we're moving into Lewis structures. Lewis structures do not involve core electrons. They involve valence electrons only. The valence electrons are the things furthest from the nucleus. They're the things that are responsible for chemical reactions. When we draw Lewis structures, they're the things we're most concerned about. All right, practicing electron configurations, though. That's what we're doing today. Chlorine has how many electrons? 17. So if I know this is my filling order, then I say there are going to be 2 electrons in the 1s, 2 electrons in the 2s, 6 electrons in the 2p, 2 electrons in the 3s. That gets me to 12. And then if I put 6 electrons there, that would take me too far. So I only have 5 electrons to put into my 3p. So this is not the proper way to write it that I've written here, but I typed it so that it would be more legible. 1s2, 2s2, 2p6, 3s2, 3p5. It's not 3p6. There aren't enough electrons to make it 3p6. Double check and make sure that you got 17. Yep. The valence shell is anything in the 3. So we would say chlorine has 7 valence electrons and 10 core electrons. If we were to write chlorine's noble gas shortcut electron configuration, you take it back to neon just the same. 3s2, 3p5. Yep. So in both of these examples, I gave you this little thing that says this is the energy of how electrons fill. But a lot of times you will see a diagram like this. This is stolen directly out of your textbook. It says electrons go in the order of the arrows. So that's how you know 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s. It gets a little bit weird when you pass the 3p point. So be careful after that point. It gets weird. This kind of diagram is something that you will see sometimes to talk about the filling order, but the periodic table is what I use most often to talk about the filling order. This over here is known as the S block. As you may notice, everything in gray is an S kind of thing. This should say 1S and substitute that guy over there. This is the S block. This is the D block in blue. This is the P block in green, except for that helium that we've already moved. This is the F block in yellow. The periodic table tells me the arrangement of energies of these shells, subshells, and orbitals. What do I mean? Let's do it with an example. If I need to give the electron configuration of germanium, I give GE. I start with 1s. I go across the periodic table. I need my laser. I go across the periodic table. 1s1, 1s2. All right, 1s2. Then I keep going. This is 2 elements right here. So that's 2s2. I keep going because I haven't run into germanium yet. 2p, I go all the way, 2p6. If you counted, there are 6 elements across here. 2p6. Keep going. 3s2. 3p6. 4s2. We're getting closer. 3d10. Yep. And then finally, germanium is the second one in the 4p block. So that makes it 4p2. 4p2. Yep. So it's got a pretty lengthy electron configuration because it's way down here, element number 32. So a neutral germanium has 32 electrons. You could go back and count and double check that you got all 32. But as long as you followed the periodic table, you got all 32. So if we were to give the noble gas shortcut, so this is the full complete electron configuration. If we were to give the noble gas shortcut, we would start with the noble gas that's on the row immediately above the thing we're targeting. So that would be argon. So we start with argon, and argon takes the place, that symbol takes argon in parentheses. Nope, those are brackets. Argon in brackets takes the place of all of those electrons, and then we tack on everything else that doesn't include argon. Note, when I rewrite them down here, I reordered them and I put 3D and 4S in opposite orders. The reason I put them in opposite orders is because this 3D is officially considered a core set of electrons because it's part of the third shell. But because 4S fills before 3D fills, 4S is often lower energy. They're very close in energy, 4S and 3D, but we fill the 4S first because the periodic table tells us to do so, at least most of the time. Okay. So my last sentence was, at least most of the time, or at least I think that's what I said last. There are exceptions to this filling order. What? Yeah, the periodic table really gives you a ton of help, a ton of hints about how this stuff is connected. But there are exceptions. Sometimes you can get to a lower energy state by filling orbitals slightly different than we just described. So these are called exceptions to the off-ball principle, and that's what I just described, the off-ball principle. These exceptions are not things I want you to memorize, but this is an example of an exception. I want you to recognize exceptions and be able to explain why they are exceptions. So I just said that we usually fill the 4s before we fill the 3d. So if something has 11 electrons more than argon, we would normally expect it to be a 4s2 3d9. But instead, it adopts this configuration of 3d10 4s1. The reason for that is actually some in the next video, but the reason for that is filled shells and filled subshells are pretty stable, and so you can gain some extra stability by completely filling your 3D. You gain more stability than by completely filling your 4s. So this copper is an exception to the off-ball principle. Again, don't memorize, just be able to recognize when there are exceptions. So chromium has 6 more electrons than argon, so we would normally expect it to be 4s2 3d4. But for some reason, chromium decides to fill its electrons 3d5 4s1. We will talk about it a little bit more in the next video, but it doesn't hurt to repeat things. A 3d subshell can hold 10 electrons total, which means it has 5 orbitals. So if you, I'm going to go leap ahead. If you put in electrons, and that's what these arrows are, I know we don't know why we're doing arrows and not dots right now. We're getting there. If I put in electrons, when I get 5 into a D subshell, we say that that subshell is half filled, and half filled subshells are reasonably stable. So chromium adopts to this half-filled 3D rather than a less than half-filled 3D. So he's got a half-filled 3D and a half-filled 4s, and that brings a little extra stability, a little lower energy to adopt that electron configuration. Okay. Which neutral atom has the electron configuration krypton 4d10? Well, we would normally expect that 4d10 comes after a 5s, but the fact that there is no 5s written right here or afterwards, it tells me there are 10 electrons more than krypton. So krypton is 36, so I'm looking for element number 46, and element number 46 is palladium. Yep. All right, so we said the periodic table gives you a lot of hints and a lot of details about how electrons fill. We have to make sure we understand where the F block really belongs. So the F block is always found, almost always found, below the periodic table, and there's this little gap that says it belongs here, but students can't always visualize what that means. This is an odd-looking periodic table that's super long because we've inserted the F block where the F block actually belongs. So now this is the D block. Let me highlight a few things. This in purple is the D block. This that I've highlighted already is the F block. This is still my S block. These two. And this is still my P. Over there. Hydrogen and helium. We really imagine helium's over here, of course. So, the row number on the periodic table, also known as period number, the period number tells me what shell I'm working with most of the time. This is 1s, this is 2s, this is 3s, this is 4s, this is 5s, etc. But 3s, 3p, all of a sudden this is 3D, even though it's one step lower than, let me see if I can make this legible. This is the 3D, nope, that's not legible at all, but maybe you saw me write it and can follow. That's the 3D row. The same odd logic applies that when you get to the 6S row, after 6S becomes 4F. So 4F is on the 6th period of the periodic table, and 5D is on the 6th period of the periodic table. It gets strange, I know, but 4S and then 3D and then 4p. 5s, 4d, 5p, 6f, 4f, 5d, 6p. Yeah, it's going through that same arrow diagram, just looking at the periodic table instead of the arrow diagram. And that's enough. I'm done.